to Data 620. This is for group number 5. We use the Snap Social Circles Facebook dataset for our week 3 assignment. This dataset contains about 4,000 nodes and 88,000 edges, but we used a pretty small sample of that since this is a pretty comprehensive and complicated dataset. The bulk of our analysis used zero.edges data file, and this is what we did. We used the NetworkX Python library mainly for our analysis, and we also used matplotlib for some of the plotting abilities. So what we did was we first imported the edge list. This data set is an edges file, and NetworkX actually makes it really easy for you to just read edge list, little command there. We noted that this data was unweighted and it was a symmetrical list between two Facebook users or nodes. Nodes are the individuals that we sort of try to capture using graph analysis and graph analysis. And so we imported that into the variable g, and NetworkX gives you this very handy function called .info, and that gave us some really quick statistics about this the edges in our data set. There were 333 nodes, and there were 2,519 edges. The edges are essentially the connections between different nodes. So how many connections there were between all of those 333 nodes. The average degree was 15 approximately, and that essentially means the average amount of connections each one of those nodes have. So we use some of the functions in NetworkX to sort of understand our dataset a little bit more. We use the shortest path and shortest path length. These are just two samples of it. We took two nodes and we tried to see how many different nodes you had to pass through to get from one to the other, and so you use shortest path length to find that this path has about 3 different connections, one from 236 to 226, another from 26 to 277, another from 277 to 294. And what we did with that was we tried to create our own little function to understand, maybe take this concept a little bit further and try to see, with all of the combinations of all of the nodes in our data set, which were 333, what was the largest shortest path, sort of like that idea of 6 degrees of separation, sort of taking it that step further with our data set. So what we did was essentially just took this zero.edges and put it into a data frame and collected all of the unique combinations between all of the nodes using inner tools combinations, very handy, nifty function there. And then we created this function called getMaxPath. So taking all of those combinations in our graph, using the shortest path length, and then trying to find the largest one. It actually doesn't take too long to run, and then we can see that the max path between all of our nodes is actually 10. So a little bit of an interesting stat there. And then what we did was we started to graph it. We used nx.graphNetwork, and then we brought in the graph there. And then we sort of noticed a problem. There were some subgroups or clusters that weren't really connected to everyone else, and so it made the data, the graph, look a little bit distorted and odd. And so what we did was we found the biggest cluster using connected component subgraphs, and that using the max function we were able to find the biggest cluster by length and then just graph that one. And so that one looks a little bit better and cleaner. It's still a little hard to understand, but we tried one more graph to really understand this data set. And so here we also found the diameter of the resulting cluster using the diameter function. Here it's 11. And so essentially a diameter is going to be the length between one node to the next, sort of like, I guess, sort of if you wanted to visualize it like this node to this other node. So it's actually kind of interesting that in the biggest cluster that we have, the diameter is 11, but in our entire network, there's only 10 degrees of separation. Okay, in this last section, what we did was we tried to make a little bit of a prettier and easier to analyze graph. A lot of this code was inspired from this really great data camp article called Social Network Analysis in Python. And so the first step that we did was we used the spring layout function that positions the nodes sort of in a nice way that you can see everything based on factors in the function, including the number of connections and the weights. I don't think that this is a weighted data set, so it would probably just be the number of connections each node has. Then we use this between centrality function to compute the shortest path between centralities for nodes. Essentially what betweenness centrality does is that it quantifies the number of times a node is in the shortest path between two nodes and shows sort of how interconnected two nodes are. If, for example, number 26, the node 26, kept showing up in the shortest path between two nodes, then you would see that it was a very important, I suppose, nodes because it really helped make things more interconnected. And that was used to find the size of the node, bent set used for node size. So the bigger the node was, the better connected it is, the higher the betweenness centrality was. And then we also use this value degree for each of the nodes. Degree is essentially defines the number of connections a node has. The average here was 15, but if a connection had more, the first node here, for example, has 16 connections, then it's going to be a little bit of a lighter color than the others would. So we use those values, those stats, to help create this a little bit easier to understand graph.